Okay, hello, and I'm going to be showing you how to do problem number 2 of the Garrett and Grisham. There it goes. Cool. Alright, so this is a problem right here. Let me zoom out for a little bit. So what we need to focus on for this problem is the 0.5, and that's going to be at 20 degrees Celsius, and 10, which is at 30 degrees Celsius. Something important to know about this is these are the KQ constants, the equilibrium constants. So how we're going to do this is it's also given us a clue that delta H is independent of temperature. So for that reason, we can treat delta H as a constant variable in our equation when we get to that. So the first part of this is it says calculate the delta G's at each temperature. Okay, so first let me just show you how to set that up. So first we're going to use our equation right here, and that's going to be delta G equals negative RT ln KQ. So the key to this equation is to use our R constant, and R is going to equal 8.314 times 10. No, that's just going to be like that. Okay. And the units for this is joules per Kelvin per mole. Okay, so the reason for that is because when we're using this equation, our delta G is going to be in joules per mole. And so if we look at our equation one more time, delta G equals negative RT ln KEQ. We can see that when we multiply our temperature by this unit, we're going to get J's joules per Kelvin mole. Okay, so now what we can do is we can go ahead and just plug and chug, right? So for what I'm going to label as delta G at 20 and delta G at 30. And this is going to be times 293, and that's because 273 plus 20, we have to convert it to Kelvin, ln of 0.5. That was our KQ given to us. This is going to equal negative 8.314 times 303 ln 10. And that's going to be another one that was given us. So after we plug and chug, let me do that real quick. Okay, so what I do get is I'm going to get, this is going to be equal to 1688 joules per mole. The book, the answer it gives you is 1.69, but that's because it's in kilojoules per mole. This is in the book. Okay. This is also page 68, problem number 2, if I didn't say that already. So this one right here, after plugging and chugging, sorry for any background noise, we are doing dishes. Okay, we are going to get joules. Ah, God, I'm horrible at writing. Per mole. Okay, so now what we can do is, because delta H is independent of time, or I'm sorry, temperature, we can set up in a system of equations delta G20 and delta G30. And this is going to equal, I have to kind of do this over a camera, so I'm sorry, my handwriting's extra bad. Delta H, this is going to be normal because it's independent of temperature, so we can treat it just like an X in any algebraic equation. Negative S T20 minus delta S T30. Okay. So as we can see, these two are equations. Now, because we have consistent variables, we can combine our consistent variables, and we're going to leave these here. So now we just plug in for what we have. So as we calculated above, our delta G is going to be 1.69 times, sorry, my thing's beeping at me. I lost my concentration. Delta H minus delta S at 293. This is going to be negative 5.8. This is the reason I wrote like this is just because it's easier to calculate. This is actually kilojoules per mole, these numbers. So all I've done is I've taken these numbers up here and moved the decimal place over 3 and give it K. 0 equals delta H minus delta S 303. Okay. So what we can do this in two ways. We can either solve for delta H itself and then plug it into this equation and then solve for delta S. But when I actually did this, and that's actually why I suggested at first, but when I do this, I actually find out that it's easier to just subtract the two equations because when that happens, the delta H just drops off because delta H never changes. Now this is this, and this is this. So this becomes positive, this becomes positive, and we're left with 7 point, I believe it's, give me one second. 7.49. And that's going to be 10 delta S. Okay, so as you can see, this is easily solved by just dividing this by 10. So we get delta S equals negative 4.9. This is going to be Kelvin. And so our delta S is going to be kJ Kelvin per mole. No, sorry. It's not going to be true. It's going to be Kelvin down here. Completely sorry. So kilojoules per mole Kelvin. And if you look at that, these units work out when we multiply delta H times T. Also, the units for delta H are the same as delta G. So the units for delta H in future problems will be some sort of joules per mole. Delta S is joules per mole over Kelvin because Kelvin, when multiplied, those units cross out and then we can subtract. Okay, so those are the 3 answers in the book, and they should be good for sig fig. Sorry about that. Again, I'm doing this is my first time, so I hope this helped, and good night.